This is one of the most famous photographs ever taken, but it holds a lie, or at least an illusion, that has fueled one of the greatest conspiracy theories in history. Look at this. Just look at it. Humanity, untethered, floating in the void. It's a testament to our ambition, our courage, our science. It's one of the most famous photographs ever taken. But have you ever really looked at it? Look past the astronaut. Look into that deep, inky blackness. What's missing? Where are all the stars? This single observation, the lack of stars, has fueled one of the greatest conspiracy theories of our time. That the moon landings were faked, that these images are fraudulent, that it's all one big hoax. People look at photographs of rocket launches, of the International Space Station, of the lunar surface, and they all have one thing in common: a black, starless sky. So what's the deal? Are they lying to us? Or is the universe trying to teach us something profound about the nature of light and the very instruments we use to perceive it, both the ones we build and the ones we're born with? The power of this conspiracy theory comes not from a single piece of proof, but from the confluence of two separate misunderstood phenomena: the limitations of cameras and the adaptive nature of human vision. The fact that both photographs and the astronaut's own accounts describe a starless sky creates a seemingly robust but ultimately false confirmation bias. A person sees a photo from the moon with no stars. That's anomaly number 1. Then they hear that the astronauts didn't remember seeing stars either. That's anomaly number 2. Without understanding the separate scientific reasons for each anomaly, the brain connects them into a single narrative. The scene is fake, which is why there are no stars in the pictures or the astronauts' memories. The strategy to unravel this mystery, then, is to pull these two anomalies apart, explain each on its own scientific terms, and then show how they are, in fact, unrelated consequences of being in a bright, sunlit environment in space. Let's start with the camera. To understand why it can't see the stars in these photos, you have to understand a concept called dynamic range. Forget the jargon for a second. Think of your camera's sensor as a set of millions of tiny buckets, and light, photons, as rain. The goal is to catch just the right amount of rain in each bucket to create an image. Now imagine you're on the moon. The sunlight hitting a bright white astronaut suit is a fire hose of photons. It fills the bucket instantly. But the light from a distant star? That's a delicate, faint mist. Here's the problem: the fundamental limitation. A camera cannot measure a fire hose and a mist at the same time with the same set of buckets. If you set your exposure long enough to catch the mist of starlight, the fire hose from the astronaut will cause the bucket to overflow, creating a washed-out, completely white mess. This is called overexposure. If you set your exposure short enough to perfectly capture the astronaut, which is the point of the mission photo, the bucket barely collects a single drop from the starlight mist. The star remains invisible. This is underexposure. This problem isn't a failure of the camera, but a testament to the extreme environment of space. It's a direct visualization of the immense difference in energy between our local star, the sun, and distant suns. The photograph isn't hiding something, it's revealing a physical truth about the universe. Proximity is power. The sun is a star just like the others, but it's incredibly close, while other stars are trillions of miles away. Light intensity falls off with the square of the distance, so the light energy arriving at the moon from the sun is orders of magnitude greater than the light energy from even the brightest star. The absence of stars in the photo isn't a digital glitch or a hoax. It's the physical, predictable result of pointing a limited range sensor at an unlimited range reality. The photograph is an honest depiction of the camera's experience. In photography, this range between the darkest darks and brightest brights a camera can capture in a single shot is its dynamic range, and we measure it in f-stops. Each stop represents a doubling of light. A typical consumer camera might have a dynamic range of 10-14 stops. That sounds like a lot, but the scene on the moon, the pitch-black shadows next to a surface brighter than snow in direct sunlight, has a dynamic range that is vastly greater. The camera is forced to choose. As photographers on Earth and in space know, you always expose for the subject. The astronaut, the lunar module, the Earth hanging in the sky, these are the subjects. The stars, unfortunately, are the background noise that gets sacrificed. The dynamic range of the subject, the actual scene, often exceeds the dynamic range of the camera. If the subject dynamic range is wider than your camera's, you will likely lose detail in the shadows or the highlights or both. It's a limitation of the camera's ability to capture the full spectrum of light in a single exposure. Okay, I hear you. All right, Neil, the camera is limited. I get it. But what about the astronauts? What about the human eye? It's the best camera in the world. And you're right. But it's also not a camera at all. It's a biological survival machine. And to understand what the astronauts see, you have to know the two different teams of light catchers in the back of your eye, the cones and the rods. Team Cone is your high-definition 4K color crew. You've got about 6 million of them, and they're concentrated in the center of your vision. They give you sharp details and all the brilliant colors of the rainbow, but they have a weakness. They're divas. They need a lot of light to work. This is called photopic vision. It's your bright light daytime vision. Then you have Team Rod. You've got over 100 million of these guys. They are your black and white, low-light, night vision specialists. They are incredibly sensitive. Some research suggests a single rod can detect a single photon of light. They see in shades of gray, but they are masters of detecting motion and shapes in the dark. This is scotopic vision. It's your things that go bump in the night vision. So what happens when you're an astronaut on the moon? The lunar surface is reflecting bright, unfiltered sunlight. Your brain goes into full-on daytime emergency mode. Your pupils constrict down to tiny pinpricks to protect your retina, and your brain switches entirely over to Team Cone, photopic vision, to process all that bright, detailed information. Meanwhile, your ultra-sensitive Team Rod is completely overwhelmed, saturated, and bleached out. They're offline. They can't help you. And since the faint light of the stars can only be detected by your rods, in that moment, you are effectively blind to the stars. Your eyes are perfectly adapted to see the bright moon, which makes them perfectly maladapted to see the dim stars. The evolutionary design of human vision is fundamentally terrestrial. Our eyes are optimized for survival on a planet with a thick atmosphere, a day-night cycle, and the need to discern colors and details in bright light. The failure to see stars during the day is actually a feature that prioritizes the immediate, sunlit environment. The space environment simply takes this design to its logical extreme. The astronauts' inability to see the stars is a direct consequence of an evolutionary system designed for Earth being placed in an alien, unfiltered environment. It's a beautiful example of biology meeting astrophysics. But there's a twist. The Apollo astronauts did find a way to see the stars. Where? In the one place on the moon that was shielded from the sun's glare, the deep, dark shadow of the lunar module. Astronauts reported that if they stood in that shadow for a few minutes and let their eyes adapt, let Team Rod come back online, the universe would slowly, magnificently reveal itself. The stars would appear. This isn't a contradiction. It's the proof. It perfectly demonstrates the two modes of our vision. So if a quick snapshot can't capture the stars, how do we get those beautiful astrophotography images we see? We have to give the camera's photon buckets more time to collect that faint, misty starlight. We do this with long exposures or by a technique called image stacking. And some of the best practitioners of this art are the astronauts themselves. Meet NASA astronaut Don Pettit, a scientist, an engineer, and an artist. Aboard the International Space Station, ISS, he took his camera, pointed it out the window, and took not one but hundreds of 30-second exposures. Then, using software, he digitally stacked them on top of each other, combining all the light he collected. And the result is this. Star trails. The city lights of Earth like a golden river. The cosmos in all its glory. The stars are there. You just have to know how to look. But what happens when you take this idea to its most extreme conclusion? What if you take our greatest eye in the sky, the Hubble Space Telescope, and point it at a patch of sky that looks completely black, completely empty? A tiny, insignificant spot, the size of a grain of sand held at arm's length. And what if you just leave the shutter open? Not for 30 seconds, but for hundreds of hours, over days and weeks, collecting the faintest, most ancient photons in the universe. You get this. The Hubble Ultra Deep Field. Every single speck of light in this image, with the exception of a few foreground stars, is not a star. It is an entire galaxy, containing hundreds of billions of its own stars. In that one tiny, empty patch of darkness, Hubble found nearly 10,000 galaxies. Some of them so distant, we are seeing them as they were over 13 billion years ago, near the very dawn of the universe itself. The Hubble Deep Field is more than just a pretty picture. It's a profound philosophical and scientific statement. It's the ultimate proof that our perception is limited, and that an absence of evidence is not evidence of absence. The underlying scientific hypothesis, the cosmological principle, posits that the universe is homogeneous and isotropic on large scales, meaning no patch of sky is truly empty. Hubble ran the experiment. It pointed at a seemingly empty piece of sky and collected data for an unprecedented amount of time to overcome the limitations of dynamic range and sensitivity. The result transforms the initial question. The question is no longer, why is the sky empty? But how can we see what's really there? So, why are there no stars in space? We've seen it's not a conspiracy. It's a beautiful collision of physics and biology. It's the limited dynamic range of our cameras struggling to capture the extreme contrast of space. And it's the brilliant adaptive design of our eyes, which switch between color-rich, photopic vision for the bright day and sensitive scotopic vision for the dim night. In the sunlit environment of space, our cameras and our eyes are simply locked in day mode. The stars are always there, in every photo, during every spacewalk. They're just waiting in the silent dark, separated from us by an abyss of brightness. And this whole question teaches us the most important lesson in science. It reminds us that what we see is not all there is, that our senses and the tools we build have limits. To truly understand the universe, we have to be humble, we have to be curious, and we have to keep inventing new ways, like Hubble, not just to look, but to see. If this journey through light and perception has left you in awe, you're going to love what we have planned next. We're going to tackle why you can't see a laser beam in space. It's another cosmic puzzle. So do yourself a favor, subscribe to this channel and hit that little cosmic bell so you don't miss our next trip through the cosmos. Keep looking up.